everybody for coming. And so my goals for this were kind of to just expose people to a bunch of different systems. And so here are the notes. So kind of we'll take a look at 3 or 4 different environments for doing this kind of live graphics program and look at how each one of them implements audio reactivity. It's a little bit different in each one of them. And so kind of discussing some of the strategies for that. And then have some fun watching some videos of some kind of classic examples of the genre of visual music that concerns itself with these types of questions of what are aesthetically interesting ways to synchronize audio and video or not, depending on who the artist is. And what are also some more contemporary examples that use some of the different tools that we're going to be talking about today. So we'll start off by doing some live shader programming using a system by Sean Lawson, who's a professor out of Rensselaer Polytechnic Institute. He has a pretty cool web-based environment called The Force that lets you do live shader programming. And from that'll kind of give us a little bit of an understanding of what shaders are and how they work. And then we'll look at 2 environments that kind of basically provide a high level of abstraction around shaders. So one of those is Hydra, that's already been mentioned here today, which is a really cool environment that lets you do things that are kind of comparable to analog video synthesis. That was the metaphor she was looking at when she created the environment. The other one is a system that I created called Marching.js, which is primarily inspired by aesthetics of the demo scene. We'll talk about that and what the demo scene is a little bit later, but basically it's a fancy way of doing weird 3D graphics, and that's what this kind of crazy looking thing is that's going on here is some demo scene-y ray-marched graphics. And so we'll look at that and how the synchronization, and we'll end with the main system that I work on in Jupyter. But hopefully there'll be a chance to kind of, for all of us to play around with all of these systems and maybe share some things that we managed to make in the span of the next few hours. Yeah, and if there's any questions that come up while we're doing any of this, or any comments that anybody wants to make, please feel free to just jump in and interrupt me or cut me off or whatever you need to do. I am very informal. Okay. So the first thing that I mentioned was diving into shader programming. So if you've never done a shader programming before or aren't familiar with what a shader is, it's basically a program that runs on the graphics card of your computer. And so it's a little bit different from how programs that run on the CPU of your computer work. So for a shader, you have these really, or typically fairly small programs that run once for every pixel on your screen. So the responsibility of the shader program, and this is a specific type of shader called a fragment shader, which is the only type we'll be dealing with today. The specific responsibility of the fragment shader is just to color 1 pixel. And then the graphics card runs that fragment shader thousands and thousands of times for every frame of video to color every single pixel on your screen. And then when it runs that fragment shader, it gives it some extra information so that you know where you're at in the screen for each pixel that's being rendered. And you can wind up doing lots of cool things with just a minimal set of information for doing this. So live shader programming has been kind of a thing in live coding performance for quite some time. And maybe before we actually go into some of this, let's look at a couple of examples of videos. Ooh, I forgot to test the sound. Hopefully the sound is going to work for me. This was the first video that got me super excited about doing live shader programming. It's by an artist named Hexler, who is off. And he actually has his own software that he's developed. It's called CodeLife. that's specifically made for doing live shader programming. Unlike the stuff we'll be using in this workshop, it's a paid software package, but it has a lot of really cool features inside of it that make doing this type of work easy. And we're actually going to do something somewhat comparable to what we'll see happening in this video. We'll start playing it. Yeah, sound awesome. So I think the really amazing thing for me about this performance is I don't think it ever gets above, that's line 16, that little program right there. There's a blank space up here, there's a comment, right? Really it's probably like max like 13 or 14 lines of code in that little shader program that are being run at any one moment in time. Again, the program is designed so that every time it runs once for, whoa, that's unacceptable.
Recommended.
Jeez. I didn't know Vimeo was so risque. Yeah, sorry.
How is the audio input getting into the shader?
So his system by default has like an FFT analysis that it does, and it sends that up to. There's a particular type of data you can send from the CPU of the computer up to the GPU. It's just called a shader uniform, and the system that we're going to use also has that same type of thing built into it.
Mm.
Yeah. But yeah, so just having a pretty minimal set of code, and we'll kind of look at how to get something that's getting close to what we just saw there. And so we'll start off just by making a sine oscillator that does some basic oscillations on the screen, and we'll gradually build up to kind of showing that kind of waveformish looking sine pattern that he had inside of there. It shouldn't be that crazy, but please stop and ask me any questions as I go through it if I start going too fast or if anything comes up. Okay, so the first thing about this, and you feel free to just follow along and code along. Again, all the code that I'm going to be using is up on that gist that I posted to the WAC Slack channel.
What else in the Slack did you post it?
To the WAC 2019.
Yeah.
I just posted it at the bottom of that, I think.
Is it a general channel?
No, so in the web audio Slack, there's a channel called WAC 2019. And it's maybe like 5 or 6 messages up from the bottom.
Oh, okay. From Charlie Brothers.
Yep. So I'm just going to copy this first block, or maybe we'll just look at it here first. For a fragment shader, they roughly all take some type of, it might be a little bit different depending on what system you're using, but really this is the general environment. You have a function that's called main, and you want to define a color. That's the result of the main function. That's all the fragment shader is supposed to do. It's supposed to create a color for each individual pixel on the screen. And so this GL frag color thing is like just a fancy keyword for what the final output color will be of the fragment shader. And then we give it a list of 4 items. The first one is the amount of red in the color, the amount of green, the amount of blue, and then the alpha values, the opacity of the final color that's presented right there. And one thing that's a little bit different that I mentioned here is that whenever you use floating point numbers in GLSL, you have to be very careful to include a decimal point. So this is not JavaScript. This is it's called the graphics language shader language, which is a horrible name. So people just call it GLSL instead. But it's kind of like an additional language that works on top of OpenGL, if you've heard about OpenGL before. To do lighting and other kind of things that are run much more quickly on the GPU. And the reason that these programs run on the GPU more quickly is because the GPU, unlike the CPU, is massively parallelized. So there's lots and lots of processors on there that can run 64 copies of this program at once, one on each processor, and that's how it's able to process millions of pixels per frame of video. With these small little fragment shader programs. So it's a little bit different than thinking about, I want to draw a shape. Now we're just saying I want to color a pixel, this one particular color. But hopefully it'll start to make sense after we play around with it a little bit. So I'm going to copy this code. And I've got a link. Oh, do I have a link? No, I just say The Force by Sean Lawson. Okay, so the link for that is seanlawson.github.io/theforce. Zoom that in somewhere and make it bigger. So this is the link for the software we'll be using for the live shader programming. And so if you want to just start off by copying and pasting that code from the GIST into the system that's here, you should get a giant blank red screen once you've done that. Everybody got that link to pop up? Sorry that I forgot to stick it in the Slack. I can also post it in the Slack if that's easier.
Yeah.
Make sure I've got it right here.
Slack was.
Yeah, okay, I'll put it in the Slack.
Sean, so it's the Charlie Roberts one or the other one?
I'm just posting it in the Slack.
Yeah, for some reason I cannot get it.
Into Slack.
Sean Lawson?
It's seanlawson.github.io/theforce. That's the easiest way to do this. I'm gonna just start using it. So that program that I had on there looks something like this. And then once it's rendering correctly, it should basically turn red. And this is actually kind of an interesting live coding environment. Both this one and that CodeLife example that I showed earlier operate on a per keystroke basis. So every time you type anything, it tries to evaluate it and recompile the shader to see if it will work, which is sort of interesting. So if you go back and watch that video, there's a link to the video we just looked at in the GIST. You'll see that a lot of times the performer will deliberately put errors into the code so that it can't recompile. And then right when the music's getting ready to change, he'll fix the error so that it recompiles and everything changes. And it sort of seems like it's magically lining up in the music, but it's actually because he's deliberately introducing errors into the code to stop it from doing recompilation. So once you've got this up, you can try just playing around with some of these numbers. So red plus green gives me yellow, red plus green plus blue gives me white. This is additive color as opposed to subtractive color. If you're thinking about crayons when you're a kid, it works a little bit differently. And so we have the red color, the green color, the blue color, and again, the last value is the alpha. Typically, you won't mess with that very much when doing this type of coding. Again, we define one main function. You can create other functions if you want, but typically there's only going to be one main function, and then we just need to pass a color value to this glfrag color in order for it to work. And it's a 4-item list with a red, green, blue, and an alpha value in it.
What does specs stand for?
Vector 4. Vector is just another fancy word for a list.
Does it mean that you have like vector 5 or vectors?
You have vectors 2, 3, and 4. That's all that are available. There's also matrix data structures in there for more complicated things and arrays and other ways you can organize data. But the vectors, there's only vec2, vec3, vec4. Okay, so the next example on that gist is creating an oscillator.
Special to make it, once it's the same as here, you do special to make it run.
No, because again, it should just change every time I type any keystroke. And if you do something incorrect, it changes the highlight. The highlight becomes like a red color to show you that there's some type of error on that particular line of code. So if you're getting some type of error there, it might be, the most likely one is that you don't have a decimal point in one of these floating point numbers. That's the error. I mean, if you're used to JavaScript coding, you never think about that, then yeah, it's super easy to forget to have the floating point decimal place there. So this next example is just going to make a very simple little oscillator. And so what is it actually doing right here? I'm defining a frequency for how often I want it to go through. Sine is just a built-in function that takes the mathematical sign of whatever value you give it. Time is one of those uniform values that I mentioned earlier. So it's a number that's being transferred from the CPU of the computer up to the GPU. So time is being calculated on your CPU once per frame of video, and it's being sent to the GPU, and you can then use it inside of there. And that's just what the author of the force decided to call it time. Somebody else might have called it phase or some other value. So for when you're using the force, if you want to know what all these different special uniforms are that the author has created, you can go down here to the bottom where there's the question mark, and that gives you a function reference. And so it'll show you various keywords that are available. And if I go to the uniforms that are listed, so again, these are all pieces of information that are transferred from the CPU to the graphics card. We can see that time is one of them, and it's a floating point value that we're going to be using. So I'm just creating a variable called color, and then I'm taking time, the current time, and I'm multiplying it times frequency. And I get this effect that we're seeing right here, this kind of oscillation in the color values for the whole screen. But this is maybe not the best oscillator because it's spending half the time being blank or being, we're not actually going through the full color spectrum for the full duration of each cycle. And that's because our sine is giving us values between -1 and 1. And really we just want this to be between 0 and 1. So we need to do a little offset. We could do 0.5 plus, and then times 0.5. Now we should get a little bit more consistent cycling between black and white here. Zoom back in, make sure that's easier to read. How are we doing so far? Questions? No questions. I see confused look, but I don't hear any questions.
This is like a shader,
Yes.
but like it's not. It's a shader. It's not like. I mean, usually there's like, or in some languages they have like a language on top of a shader, and then it just converts to shader like Hydra. This is like a shader.
This is what Hydra compiles behind the scenes, right?
Yeah,
So Hydra and Marching.js, they both take the JavaScript that you write, and then they use it to compile a shader. So this is the lower level language. Exactly. Okay, so there's bias, blah, blah, blah. What's the next thing? Okay, so the next thing we want to do is actually...
I want to ask a question.
Yeah.
I'm trying to add a number to color, but I can't. I think it gives like a syntax error or something. If you want to do like besides that backward, you want to add like +3 or something to a color. Yeah, I try to do that, but...
So that gives an error, but as soon as I put the decimal point, then it's okay. It's,
yeah.
you will do that many more times today, so just, yeah.
You said that
I,
1,000 times,
yeah, it's kind of like forgetting to use the triple equals in JavaScript. You're like, oh, I did that again.
Frequency.
Okay, so what was the next thing? Oh yeah, the position. Okay, this was what I meant to do next, but I have the wrong code in the GIST. So the next example that's in the GIST uses the current position of the pixel to kind of create this effect that we're seeing right here with the stripes. And so that position comes from this function called UV, which is a function that's just built into the force, and all that does is it gets the current position of the pixel. It's not a standard GLSL function, it's just something that's built into the force. Other systems will have different ways of getting access to this information. But this UV function will return a vec2, so a point that has an x and a y value, and then we can use that x and the y value to change the colors that are returned. So again, this program is being run once for every pixel on the screen. Every pixel is going to have a different p.x and a different p.y value, and we can use those values to create variation over the space of the canvas that we're dealing with here. If I change this to be p.y instead of p.x, now we have this kind of vertical scrolling that's taking place instead. And then I think when I first loaded this, I had something like this, where I was just kind of playing around with multiplying or dividing the p.x and the p.y values, and you get these kind of weird moire-like patterns that pop out of it. And I think the fun thing is once you start getting these little programs that have some small amount of complexity and then to them, you can just kind of start tweaking the different values and playing with them and seeing what happens, and fun things kind of pop out